So question 1B is saying a 2000 kilogram rocket has a net propulsion force of 550 newtons. Over a short period of time, the rocket speeds up uniformly from the initial velocity of 45 meters per second to a final velocity of 55 meters per second. Assume that the mass of the rocket remains constant even though it is burning fuel and that the net force is along the direction of travel. What is the net work done on the rocket in kilojoules? So if we look at the data that have been provided in this question, we have the mass of the rocket, which is 2,000 kilograms. Then we also have a propulsion force, which is 550 newtons. And most importantly, they've given us the initial velocity and the final velocity. And what are they looking for? They're looking for the work done on the rocket in kilojoules. So with this data that we've been provided, the method that we can use to calculate this formula is actually what we call the work energy theorem. And with the work energy principle, it's this to say the work done is equal to what? It is equal to the change in kinetic energy, which gives us what? The work done is equal to final kinetic energy, which is KE final, minus initial kinetic energy, which is KE initial. So you can put an I or a zero there. It's one and the same thing. And you know to say the formula for kinetic energy, KE, it is equal to half mv squared, like that. So what are we going to do? We've been given the initial velocity to say v0 is equal to 45 meters per second, and we've been given the v final to say it's 55 meters per second, and the mass is constant. So we can use that information to actually calculate the work done on the rocket using the work energy theorem. So I'm going to say my work is equal to KE final minus KE initial. Then what is my KE final? My KE final will be equal to half mass. What is the mass? The mass is 2000 multiplied by the velocity, which is the final velocity squared. So I'll put it in brackets, squared. This minus half multiplied by the mass, which is 2000, multiplied by 45, like that, squared. Okay, so let's continue with the calculations down here. Okay, so what will be our KE final? We're going to find to say if we multiply half multiplied by 2000 multiplied by 55 squared, we're going to get a value which is equal to somewhere 30, 25, 0, 0, 0 joules. These are joules, remember. And what about the other side where there's KE initial? We're going to get minus 20, 25, 0, 0, 0 joules, like that. So if I subtract these two figures, I'm going to get a value of 1, 0, 0, 0, 0, 0, 0 joules. So that's something like a million joules. Okay, so that's a million joules, but in the question they've specified to say our answer should be given in kilojoules. So what should we do? We're going to divide this guy by 1000. So 3 zeros gone there, 3 zeros also disappear there. Then our answer will be what? Will be 1000 kilojoules. And that is the work done. Okay, so that is all on question B. Our final answer we've reached using the work energy theorem. We found to say it is 1000 kilojoules. That's the work done on the rocket. Thank you for watching. You can actually like and subscribe to the channel. Thank you.